Let's look into some of the fundamental and very important concepts of complex numbers. I generally consider this as the body of the complex numbers because it helps us to solve many of the questions very simply, very intelligently, and without any rigorous effort. Okay, so let's look into what is modulus and conjugate. So let's take a simple complex number. Let's say z1 equals to a1 plus iota b1. So first let's introduce what is a conjugate. So the conjugate of a complex number z1 will be simply written as z1, and this is bar by just a simple line over the number, which will be equal to a1 plus iota times negative of the imaginary part, that is minus b1. Okay, so let's simply look into an example. Let's say z1 is equal to 2 plus 3 iota. Sorry, z1 is equal to 2 plus 3 iota. Then z1 bar will be 2 plus iota times minus 3, which is simply is equal to 2 minus 3 iota. It is simple to see, and let's now go to the next concept, which is that of the modulus, which says that mod z1, this thing is called mod z1. It may sound similar to that of the absolute value. In some sense we'll revert back to that thing in later part of video, but conventionally it is it's just take it in the same sense. Okay, so it gives the magnitude of the number z in when you represent it geometrically, as we'll do in the next slide. So just to get the first of all, let's just get the formula right, which is mod z equals to under root of a1 plus b1 square, that is under root of real part square plus imaginary part square. Okay, so as you would have noted that when you multiply z1 with z1 bar, sorry, z1 with z1 bar, you will yield a1 square plus b1 square, as iota square will be equal to minus 1 when you multiply these two numbers, which is same as mod z square. This property is pretty important, and I would like you to just practice this. Okay, okay, so in this slide we'll work out how to visualize what is a complex number. Since now you've been very clear of what are complex numbers. Okay, so now let's get a pictorial feel of what are complex numbers. To get that, just let's say it consists of let's first of all do the graph part, that is representing the complex numbers on the plane. So to represent complex number, what we do is that we consider the 2D plane, and we call the 2D plane as Argand plane. Okay, and what are the coordinates of that particular point? Let's say if we are representing a complex number, say z1, which is equal to a1 plus iota b1, then the point z1 to represent in the Argand plane is equal to the point which corresponds to the coordinates a1 comma b1. So z1 will be a point which corresponds to a1 comma b1. Okay, so let's say here we have a complex number, say x plus iota y. So it will be represented by this point, this particular point, p equals to p comma px comma y. Okay, so as you can see, this line, the magnitude of this length will be equal to under root x square minus y square, which, as you've learned in the previous slide, is equal to mod z square. And the angle which it makes with the positive x-axis will be theta, which will be given by tan theta is equal to y by x. So let's work out another representation. Till now we have been considering the complex number as a1 plus iota b1. Now let's work out the complex number in the polar form. So in the polar form, the complex number is represented as r whole into cos theta plus iota sin theta, where it has two parts, we had two coordinates there, that is x and y. We have r and theta in this particular form. So r corresponds to mod z, which is equal to under root x square plus y square. Okay, and theta corresponds to the angle which it makes with the positive x-axis, which lies between minus pi to pi. Okay, and as you can simply say, just multiply r inside, you will get z equals to r cos theta plus iota times r sin theta, and by comparing with the standard form, you'll get that the x coordinate or the real part is equal to r cos theta, and the imaginary part is equal to r sin theta. Okay, so just keep in mind that this particular quantity, the r, is always positive. Okay, and this corresponds to only the principal values. Okay, you could have any multiple of pi here, or say, for example, if the theta if the number is completely imaginary, you could have theta as pi by 2 or pi by 2 plus 2 pi and so on. So there are many values of theta possible, but this particular range, if you have theta in this particular range, it's called the principal value. Okay, so let's work out a simple example. Let's say if we take z is equal to let's take the number as 1 plus iota simply. So as you can see, the r of this number will be equals to under root 1 square plus 2 square, which is equal to root 2, and theta will be equal to tan inverse y by x, which is equal to 1 upon 1, which is tan inverse 1. So which is simply, as you can if you have studied in the the trigonometric part, it is equal to pi by 4 in the radial form. Okay, so the number will be represented as, which is the same number can be represented in the polar form as z equals to root 2 times cos of pi by 4 plus iota times sine of pi by 4. This is extremely helpful when you, let's also give the Euler representation of this number. When you represent this number in the Euler form, you write r and theta, and this particular part is written as e to the power iota and theta, which is here equals to pi by 4. It if you want to calculate very high powers of z, it's the suggestion, and when you want to calculate the higher powers of z, it's a suggestion to use this particular form instead of multiplying the numbers one by one and so on. Now we come to the application of the complex numbers. So let's first of all give what is the fundamental theorem of algebra. The fundamental theorem of algebra says that a polynomial of degree n has n roots. The roots can be real and complex. As in the earlier classes, you might have worked out very many examples of say a cubic equation, a quadratic equations, but you might have got stuck in the point when the quadratic equation, say let's say if you have a quadratic equation of the form x square plus 1, you would have got stuck, say, because what the discriminant of this particular equation would come out to be b square minus 4ac, which is equal to 0 square minus 4 into 1 into 1, which is equal to minus 4. So it's less than 0. So just you might have got stuck at this point. So now you have a particular tool, that is iota, or simply let's take the complex numbers to represent solution of these equations. So okay, so to get the feel of what the solution of this equation will be, okay, there's a further requirement that a and b and c should be real coefficients, okay, and a should not be equal to 0. Otherwise, as you could simply see, if a is equal to 0, then x will be a real answer, and c x will be equals to minus c by b. Okay, so if a and b and a b c satisfy this condition, then and the discriminant is less than 0, which is sorry, this is b square minus 4ac, then roots are given by x equals to minus b plus minus iota times root of 4ac minus b square upon 2a. This particular term is the thing which is changed from the general thing, as you might have learned in their earlier classes, that is minus b plus minus of under root b square minus 4ac upon 2a. Okay, so I'm not working out any examples of this particular thing of solving quadratic equation. It's quite simple, and you have to just plug in the values of ABC to solve the equations. Thank you.